All right. Hello, fellow participants. This is a second technical walkthrough with CircuitDAO team. And today we are going through the in-scope code or through the code base itself. Going to start high-level overview, then probably going to dive into some code, and then going to cover known issues and any previous findings in previous audits. And we're joined by Nick and Sebastian as in the first recording. So Nick, Sebastian, please take it away with the walkthrough. Thank you.
Yeah, cheers, Tim. Yeah, so today we're looking at the actual protocol after that intro into Chia Lisp yesterday. So what we have here is basically an overview of the various different coin types of circuit protocol. I think we already mentioned it's a CDP protocol. It's broadly inspired by MakerDAO, especially the single collateral version that existed in the very beginning. So what Circuit does is allows users to lock up some of their Chia tokens in a smart contract and borrow Bytecash against that. Bytecash is a stable coin, one-to-one pegged to the US dollar, and it's natively issued by Circuit protocol itself. And this process is basically shown here at the very bottom of this diagram. So borrowers basically create their own vault coins, collateral vault coins, we call them. And these are the coins where they deposit Chia tokens and borrow and repay Bytecash. Just as a quick reminder, Chia was a stateless chain and it's UTXO model, so everything basically is a coin in Chia. So each borrower, essentially, it's quite straightforward to create a new vault. All you need to do is create a coin, basically, that's got the vault puzzle inside it, and that's it. So it's pretty straightforward and actually conceptually quite clean from that perspective. Another kind of thing that users can do is if they don't want to borrow, what they can do is they can actually take Bytecash that they can, for example, buy in the market for US dollars. They can take the Bytecash and lock it up in a savings vault. So principle is the same. Each user creates their own savings vault coin, and that coin accrues interest over time. And the interest that's being paid to savers is essentially raised in form of stability fees, so basically interest rates charged to borrowers. And in between sits the treasury. That's basically where the protocol accumulates any sort of surplus that it makes between the stability fees it charges to borrowers and the yield it pays out to savers. And over here on the right, we see a bunch of different auctions that can take place. Maybe the first one to look at is the liquidation auction down here. So liquidations take place on collateral vault coins, and they happen whenever the amount of collateral, so the amount of Chia locked up in one of these coins, is no longer sufficient to, or no longer sufficiently over-collateralizes the amount of Bytecash that has been borrowed, or more precisely, the amount of debt that the borrower has incurred. So the debt is basically the principal amount of Bytecash that was borrowed initially, plus accrued stability fees, that sort of grow and grow over time. A liquidation auction does exactly what it says. It basically seizes the vault from the borrower and then auctions off the collateral to recover the Bytecash. So it's a liquidation of the collateral in the vault. Anyone can basically do that. We expect this to be market makers, so kind of keepers that run bots. Therefore, this little funny guy here with robots. So these are things where we expect bots would usually do the job. Liquidation auctions are Dutch auctions. Again, this is sort of a feature taken from MakerDAO 2.0 actually. So they introduced that. And yeah, it's quite a nice way to do a liquidation auction. It kind of incentivizes people to bid quickly and not play games and with sort of delaying bids and that kind of thing. Yeah, so bids are being placed until either all the collateral is gone or all the debt is gone. If there's bad debt, it can basically be reconciled by taking byte cash out of the treasury and burning that. Again, that's the keeper operation. Anyone can perform that. And then we have two other auctions that operate on the treasury. One is a recharge auction, so that's something that you would do when the protocol really has run into bad debt badly and can't really is basically short, has operated at a loss. So this should actually ideally never happen. If it does happen, if for some reason the market went haywire so quickly that the protocol went underwater financially, a recharge auction can be held, and what basically happens is the protocol mints PRT, its own governance token, and auctions that off for byte cash in order to fill up any deficit. And the surplus auction is the opposite. So when the protocol is profitable, which typically you would expect, then over time the surplus that accumulates in the treasury can be discharged. And so the protocol sells off byte cash in return for circuit tokens, and these tokens simply get burned. So it's basically a bit like a buyback. You buy back the token, you burn it. So in the end, we expect CRT to be deflationary in terms of its supply. Yeah, and the second half of this diagram, the upper half, what we see here is, maybe we can start here in the top left, governance processes. So Circuit is also the governance token. What people can do is make proposals to change certain parameters. We call them statutes, and these parameters are basically designed to allow governance to fine-tune how the protocol behaves. So most of the puzzles, most of the smart contracts are pretty much immutable. And we have, I think it's about 40 statutes that governance can change. So these are parameters, for example, in terms of how long do these auctions run, what's the liquidation ratio for collateral vaults, and also setting interest rates here for stability fees and the savings rate. Yeah, I'm not sure, we don't need to go into more detail right now. So basically the point is people can vote with their circuit tokens, proposals can be vetoed, and if they don't receive a veto, they get enacted. And that basically means the statutes coin, which is basically a singleton that's central to the protocol, which holds all the statutes in its state, gets updated. So in a way, you can think of the statutes coin as the global, as containing the global state of the protocol. Yeah, and then the other half of this here is basically the oracle that we've built that feeds the chia price, so the chia versus the dollar price into the statutes coin. That's necessary for liquidation, so that's why we need to have this oracle in the first place, so that the protocol knows when these collateral vaults down here need to be liquidated to prevent under-collateralization. The oracle in itself is a singleton, and its price, the price we store in here, is basically made up of a number of price feeds that come from these, we call them announcer coins. So each announcer has a data provider, so an entity that's reading off-chain data from centralized exchanges, well, potentially some on-chain data as well from AMM pools, etc. And yeah, what happens in an Oracle price update is a keeper can come along, basically pick a number of these announcers. The Oracle will calculate the median price, and that basically becomes the new price, which can then be fed into statutes to be used throughout the protocol. One important feature here, maybe worth mentioning, is that there's a price delay, so that if for some reason something is wrong with this Oracle price, that there is a small amount of time left for example, governance to jump in and do something about it. So it's sort of an emergency delay that allows some sort of emergency intervention. And then the last thing we haven't talked about yet is the registry coin up here. This coin is designed to reward announcers with some CRT, which the protocol mints. And the CRT is basically given out for announcers that have been doing their job and who have been contributing to this Oracle price update process. So they can, periodically, they basically register the announcers in the registry, and in return they can mint, every, well, again, governance can decide, but every few weeks or so they can claim some rewards here. Yeah, so I think that's it from a high-level perspective. Yeah, I think if you have a read through the documentation, there is, again, an overview here of the different coin types. And basically, these different coins, they all have their own sort of inner puzzles, I think, that we're going to have a look at now. Yeah, and then the documentation basically breaks this down for the different coin types here. So if you go liquidation, yeah, you can read up on how this works in detail. So these are the kind of coin spends that are quite typical for what's happening in a coin set model, because these different coin types are sort of isolated in their own coins. So whenever you have a sort of operation on the protocol, it usually means you need to spend multiple coins in parallel, and then these coins communicate with each other by messages and announcements that we talked about in the first video. Yeah, I think maybe, shall we move on to the actual code, Seb, or did you have any other comments here? Hello?
Sebastian, are you with us?
Can you hear me? Oh,
yes.
Okay, sorry.
Oh.
Let's see. Yeah, let's just do the code. I'll just try to share. Not sure why I can't. Oh, here we go. Yeah, I think maybe we can start with statutes, as that's sort of the main singleton that holds all the state. And the way it works, yeah, we have some. Maybe I'll just go through. It's a normal module, and it has some variables. So it stores all the modules that are allowed to do things. And it's important on what index they are in this list, but essentially it's a list of hash. Well, it's a hash of list. And then we have operations, which is the operations of this module. Why we do that is that so we don't have to store all the code in the top module. So on the statutes, we can pass the extra code through the solution here. In terms of mutation, I'll show you down a few lines below. Then we have previous announce, which is a flag. If this coin has been spent before in a announce or not, which is important. in terms of replaced by fee transactions that can be done. We don't really want somebody to spend the statutes multiple times in terms of announcing and mutating. We want the mutation to happen only once in the block, because we don't want people using old announcements to approve certain things. Statutes is basically a list of statutes that hold all the values that we use across the coins. Price information, this is the current price information from the Oracle. This is the cumulative stability fee that we calculate whenever we update the price information. And it accumulates over time, which is then used by the collateral vault. Price update counter is just a counter that increases for every price update, which is then used when we reward announcers. So the more updates, the more rewards they get. And it also defines the interval, or how we reward. And this is a solution which is mainly used for mutation. So when we mutate statutes, here are some methods. This is for announcing. It iterates through all the statutes and creates announcements. Main create coins. So this is to recreate the coin. So coins are essentially, it's like whenever you spend a coin, you have to recreate a coin, especially for singletons, because we basically want continuity. And this is the main entry point, which is an assign. And assign is a statement that assigns, creates various variables, and you then decide. So we basically, this is the left side is the variables, are the variables. In this case, we unpack a list with 3 variables. And we check, okay, if we have a mutation, then let's unpack, otherwise just do a empty list. Here we have trying to get, if there's an operation, we hash the operation and then check if this operation is actually part of the operations that this coin supports. And if it is, we basically run it with we apply the inputs that we got from the mutation solution, and we apply it to the mod. And this basically runs it and returns back either updated statutes, other variables that we then apply when we call the create coin. So when we recreate a coin, those that are returned are then applied. And here are some announcements that we always do, which is about the price updates, counter, approval hashes, etc., which are used by other coins. This is essentially, this is, you could say, a state oracle. It's always just sort of announcing these parameters, and other coins know that they can trust it and verify these parameters by asserting these announcements from statutes coin. So if we go into mutation and update price, so we have 2 operations for statutes. So with mutation, here we first filter through conditions that we can support, and we filter out any that we don't support or that are could be malicious. For example, send messages or receive messages is valid condition. I think mainly checks that it's the size, and it starts with a specific character that's reserved for our protocol. Then the interesting part here is Well, essentially, these mutations or these operations, they return back the state of the statutes and any additional conditions it needs to append to the original conditions of, and this is the first, this is the list. So we say the previous announced nil. Well, this is, I think, self-explanatory. Yeah, I think that's for the mutation to happen, we need to receive a confirmation from the governance. And in this case, we say, okay, for this to happen, we have to receive a message from a voting puzzle that has to be in a specific state. Here we query the governance puzzle hash, which we generate here with specific, but essentially we're mostly interested in this because the only way that the governance puzzle can send a message in this form is if it went through the various stages of going through a veto period and then be enacted, and then going through waiting periods and etc. and getting to be enacted. That's about it. Here is the update price. Again, here we're doing a few more things than before. We're just leaving all this information intact, same as before. Here in update price, we are actually calculating all these things, updating to the new price, calculating the cumulative, updating the price counter, and returning, but we leave statutes the same. Here, instead of confirming from getting confirmation from a CRT puzzle, we are getting it from Oracle. So here we have to generate Oracle, which is also a singleton. So we just generate a puzzle announcement or assert the puzzle announcement that we get from it. That's about it. There are some certain conditions where we can only update the price if the current price have been if there was a certain delay that passed before we update, so we don't update constantly, as that would be pricey. Yeah, that's it. Did I miss anything, Nick?
No, I don't think so, no.
Shall we go to collateral vaults? Maybe. Collateral vault is, the structure is similar. We have operations. In this case, we have about 8 operations. So we have deposit, withdraw, mint, byte cash, repay the debt, liquidate the vault. So the top 4 are owner operation, and the bottom 4 are keeper, or basically once the liquidation starts, that's the protocol takes over. The collateral vaults need to be first launched, and launching means that, let's see, the standard, again, we start with the sign. We get, so each of these puzzles that are sort of dependent on statutes get a statute struct, which contains information of the main statute singleton, and is used then to assert that the certain parameters that are passed into it are correct. And this is sort of how statutes maintain control over all these puzzles. So we initialize these basic parameters like statutes, get the conditions that are passed into from a solution. Well, maybe I'll just go here. So we have the statutes, we have the collateral, that's essentially the coin amount. So how much XCH or Chia has been locked. The principal is the debt that has been minted. Auction state is keeps the auction, well, basically auction state if it's running. Inner puzzle hash is the puzzle of the owner, or how owner wants to lock this vault. Usually it's going to be standard, using the keys, public keys and stuff. And the discounted principal is a way we keep track of how much fees they owe us, and is calculated whenever they can repay a byte cache. So here again we get the operation mod, operation hash. We check that the operation mod hash is contained as actually a valid operation that can be run. We check that if this is a keeper or non-keeper, and run accordingly. We generate the puzzle hash of the currently running statutes based on what was passed to us through the solution. And then we basically run the operation. The operation, again, returns a new state of the puzzle here, which is then embedded into this create coin new puzzle of this coin. Here, maybe I'll just go back to how we started at the launch. If we don't have any lineage proof, so in the beginning, so when this coin is created, there is no lineage, essentially. There's just one first coin. We run this assert my puzzle hash, which, actually, no, this is after. We run this assert my puzzle hash where we make sure that all of the variables or all of the states of the vault are 0. And that's sort of how we want to start. Otherwise, there could be obvious issues with the balances and stuff. If the lineage proof is there, then we just check that there's the bond or the connection between the previous coin and our coin is holds integrity, as in they both use the same mod hash and variables that we're currently using to make sure an attacker wouldn't be able to use a parent that creates a new coin with a different kind of a module that is then would be able to take over every altcoin and do some weird things, like it would be able to allow minting or whatever. So essentially, using both assert my parent ID and assert my puzzle hash maintains integrity between different instances of coins. We always also make sure that the collateral that is curried in the puzzle hash is actually correlated with or the same as the actual amount of the coin, which we do with this condition. And yeah, that's that. Let's do maybe vault borrowing. Not sure if, like, we just had the first puzzle and we have 20 minutes left. maybe we should.
Yeah, it's that sounds exciting, but we're running low on time. Sebastian, so let me ask you this: what would be like the pieces of code that you believe are the most vulnerable for some type of attacks? Like, where do you think main vulnerabilities may lie here?
Right.
Yeah, like where should whiteheads start first, and go second, look third?
So I think maybe we'll go. I think we did statutes, and I think that's a good place to start because it's so central to everything. The other one is our circuit token. And this is the tail that is run by the cat, and this is sort of the sides when the CRT is going to be minted or melted. And this is also super important that it's secure and is not, doesn't have any exploits or potential attacks. And here, the tail essentially checks and allows only certain coins or puzzles to melt or mint. And in this case, it's for circuit tokens, it's surplus auction. So whenever we have a protocol has a surplus, it will sell it for CRT tokens, and then those tokens will be melted or burned using this tail. So I think in terms of security, these are really important. The tails and also the byte cache tail, which does the same thing. It allows or disallows melting given certain conditions. It's usually for byte cache, it's mostly Volt that can melt or issue new ones. The other places that's important is Oracle. If Oracle doesn't work, and then somebody can manipulate the price and trigger all kinds of many liquidations of the protocol. And with CRT tokens, it's not just the tail, it's also the governance puzzle, which is this. And the way the governance works it's really important because you can then manipulate the statutes or just take over the protocol completely. And as Nick mentioned before, the way it works is we have the CRT tokens. They can create a proposal by using this governance puzzle in it, and then starting a proposal. So let's see. Just basically propose a bill, and this bill. So we have a standard. So we have the amount on the new bill, etc. And this is sort of what we want to propose. So we want to change the index bill this much. The new value should be that. The threshold is if we're changing how many CRT tokens you need to actually even propose. The veto seconds, so how many seconds do you need to wait until this bill passes, and what's the delay after it passes before it can be actually enacted, and the delta. Delta is how much the value can actually change. So we basically limit that nobody can go from 150 liquidation ratio to 5,000 or whatever, or 10. And the current statute is basically providing what's currently, and this is the new one. Once this is done, so if this is run and everything is fine, and the user has the proposer has enough coins and all that, it goes into a veto period or veto state. And in that case, somebody with more CRT tokens than this coin can essentially veto it. And that's sort of the idea. There is also some fees that are required to be paid to actually propose. So you can't just propose all the time. This is controlled by the statutes, but the idea is that, yeah, you can't spam the proposals. Just what else is there?
Maybe one other point in terms of where could there be sort of bugs still hiding. I think it might be worth checking all the math operations again in terms of interest rate calculations, and I wouldn't be surprised if there's still sort of such a, rounding issues are quite often a source of exploits. So that's definitely worth looking at, I would say. There's already a few subtle things which we spotted. So, sometimes we manipulate the timestamps a little bit when calculating interest and stability fees, because you could otherwise do like little cheeky things like, for example, borrowing things in the future and repaying them in the past. So there is looking at sort of timestamps and arithmetic, I think that could still be, I think there could be issues there.
Yeah, so sort of where the math happens is it's just here, and in the previous file it's an include a utility library, and what Nick was talking about is here where we have a slide when we're checking the time, but I think we're talking about maybe the borrow one. This one. So, for example, as a maybe you can explain based on this.
Yeah. So here the case. So when we're repaying, we are making sure. So we are calculating the accrued stability fees, assuming that we're actually 3 blocks into the future, and that simply makes sure that, because this current timestamp is actually checked against the block time, but we don't necessarily know in advance what exactly the block time is, and also we give a bit of leeway so that if a user just misses 1 block, they don't have to create a new transaction, but it stays valid for another block. So I think we actually have 2 max block times, I think, as kind of the leeway, right? The timestamp can be either 120 seconds too far in the future or in the past. And by manipulation, so if you were doing that on purpose, you could basically by wriggling around this timestamp, you could do things where you borrow in the future, you repay in the past, so effectively you get paid interest. And by adding on these 3 max block times, this makes sure you always get charged 3 extra blocks, so more than you can gain by fiddling with this, by manipulating this timestamp here. But then I think it's important to check that obviously the discount factor is calculated properly, and so there's a lot of kind of rounding edge cases. And the way interest rates or stability fees are calculated is always by looking at the principal value and then this discounted principal or discounted savings balance, and then you undiscount it and you take the difference between that and the principal or the actual balance, and that is your accrued value. So if you do things with very small amounts there, right? So a lot of sort of subtle bugs or exploits are around, what if I do sort of edge cases, and then can I execute an edge case, I don't know, 100 or 1,000 times to actually make it sum up to a significant error? That can, in the worst case, allow me to drain an entire bolt or something like that. So yeah, lots of everything. All the mass in GLisp is integers, so all the divisions here are integer divisions. I think by default, GLisp, the division operator, rounds down. I think it's all on the documentation pages that we showed you last time. So it's worth having a read through that. And really kind of making sure that this can't be exploited in any way by, providing silly solutions and tiny amounts of collateral, or taking out tiny amounts of debt and getting into edge cases.
Maybe we should also mention one of the exploits that the auditors found.
Yes, that
Yes,
would be
good idea.
amazing. Auditors' findings, Jens, and any type of known issues that are in there, if you have any, of course.
Known issues right now, don't think so. But in terms of the issues that they found, which one should we go for?
Yeah, I think there's faking the carried mod hash, right? I think that was maybe the most interesting one.
Was that in governance too?
Well, I think it applied almost everywhere, right? That's why we applied, why we added these set my puzzle hash conditions everywhere. I think they spotted it originally in governance, but I think there's a problem everywhere.
Yeah, I'm just trying to find which branch we should use there to just see the problem. Essentially, it was just this, right?
Yes.
It was mainly what I was talking about before. If a parent, if we just check the parent always, that means that the current running could actually have a different module that's being run. If you can do that, then you can essentially be running any code that then just recreates this another like fake, basically creates a legit governance puzzle, which then recreates again a malicious governance token. So it can, because we're just checking the parent, the current one could be malicious. And I think that's sort of I can't remember what was the exact attack anymore.
I think the attack, the way I remember it is they basically had a parent coin which had a malicious puzzle and had the matching malicious mod hash carried in. So that's basically, that can be anything. So from that coin, they create the actual governance coin, which has which uses the correct governance puzzle, but has a malicious mod hash carried in, right? So the parent, because the parent is all malicious, it can do that, right? And because you had this combination of correct governance puzzle, but malicious carried mod hash, you could basically prove the prove lineage, because the lineage calculation uses the curried mod hash. So that the lineage check passed, but it passes with a mod hash that's not actually the puzzle's actual mod hash. So that was, I think, how the exploit worked, right? And then you basically ended up with something here that didn't have to be a proper governance coin anymore.
I'm not sure it's easy to follow that. Probably something to draw. But I think what's important is that the curried parameters are malleable, as in somebody can just create these puzzle hashes and just put them in the coin, and they can be just created at any certain point. And if the puzzle hash doesn't check that it has been run in the previous instances, so if there's no assert my parent ID, somebody could just create a puzzle that's shown as if it's been enacted correctly. So it could just create a new puzzle that has an enacted bill in it, and all it needs to do now is just approve by sending a message to statutes to update the parameters. And all these coins have this sort of issue that they need to have rigorous checks of the parents, of current puzzle hash, etc., to make sure it wasn't just somebody curried a new puzzle and just created a new coin with it and off they go. So that's sort of inherent to the way CoinSet works.
Yeah, and I guess in a way that problem exists both vertically, right, in terms of sort of from parent to child. We need to make sure that the lineage is correct, as well as horizontally. So if different coins or different coin types are communicating with each other, we need to be sure that when we are sending these messages, so for example, I don't know if you can scroll down a bit on the, there. So here, for example, the governance, where are we at? Governance, so we're sending a message to the statute's puzzle hash. So how do we know that this statute's puzzle hash is actually the puzzle hash of our statute's coin, right, and not something that the governance token owner made up, right? So where does that come from? It's probably passed in from the main puzzle, is it?
Yeah, so
up there. Okay. So and then the governance main puzzle constructs the statute's puzzle hash somewhere. Yeah, and it uses the statute struct, which is basically the singleton. It's a carried arg of the kind of standard tier singleton that we talked about last time. So that's basically, that ensures that the statute's puzzle hash cannot just point to any random coin, but it has to be the actual statute's coin that this governance token is tied to via this struct. So this kind of stuff happens a lot, and the question always is, have we made sufficiently sure that this can't be gamed in any way, right? So I need to make sure that the coins, that nobody can slip in a coin that pretends to be some other coin and starts sending or receiving messages, and thereby deceiving another coin and getting an operation to pass that shouldn't pass, etc.
Yeah, all coins should be under a specific statute struct umbrella, and they should sort of check that as they communicate between each other that they are under the same statutes, and not just basically somebody could launch a new protocol, for example, version or different kind of a statutes, and then communicate with our coins if we wouldn't check that the statutes match. Because it would look like, okay, it is a coin and it's running and it's a collateral, and now this collateral vault will be issuing bytecash on another protocol and stuff like that. So need to make sure that everything is under the same, like, let's say, namespace, which is defined by statute struct, essentially. Mm. Yeah, I mean, the last thing is probably announcers that are probably more important than the rest. Or maybe treasury, what do you think?
Yeah, maybe it's announcers is a good one to talk about.
Announcers hold the price, and they will usually every 10 minutes or so, or if there's a change big enough, they will mutate their puzzle, which is this. Essentially, just holds a value. Actually, I should go to they hold a value, and they change this value every 10 minutes or so. And once time is passed, they can be used to announce. And in an announcement, they basically just say, hey, this is my value, and I have a flag that's approved or not approved that is defined by governance. So governance can look at some announcers that are announcing prices and check, okay, they're legit, that's fine, let's approve it. Once they're approved, they can actually, at that point, they can register to get rewards. But here, essentially, they just create a puzzle announcement, which they announce the value and that they are approved. Each of them has a launcher ID, which is a unique ID for them that you can identify them by, and also have to keep a rigorous linear checks. So all that applies to this too. They can mutate the price to whatever they're getting. The Oracle then uses a median of all the reported prices and that price is then actually used in the statutes. In case an Oracle aggregates these prices, and it will have a queue of all the prices that need to be applied on statutes over time. Like we're probably going to go for a 1 hour delay. And in that 1 hour, if governance or somebody notices weird prices in it, there's a time where we can reset the Oracle so that if, for example, all announcers are malicious and they're starting to push very low prices because they want to trigger liquidations or anything like that, the governance can step in. And announcers have to deposit certain amount and can be penalized if they start missing price updates. But they're crucial to the system as all the prices feed into collateral vaults, into everything. I think that's about it.
Wonderful. We're just at time. Sebastian, any last thoughts? Anything you want to add?
Not really.
Okay. Then, we can call it a day. Again, this recording will be shared with the participating whiteheads very, very soon. So, Sebastian, Nick, thank you so much for the presentation. And good luck, fellow participants. Thank you.
Thanks.